Good evening, ladies and gentlemen. Thank you for joining our meeting. And this is our result of paper that we have conducted about sensors and automated filtration systems for beta fish. Well, first of all, my name is Claudio Julian Kurnia, and my friend Samuel Yedija Purnomo. I will conduct the meeting by myself. We are both from Bina Nusantara University, Bandung campus. Please enjoy our presentation. Thank you. So, table of contents that we are going to conduct is about beta fish, its water tank, filtration system, water sensors, workflow, data and results, and the future AI implementation. Why do we pick the particular experiment? Is why if beta fish are well known for their unique yet elegant, vibrant colors, particularly their fins and types, but scientific features come with a tool that's extra care for their living space. Requirements for a healthy, clean water is environment to survive. It's essential because it's exposure to poor water quality are prone to stress, disease, and death. And maintaining beta fish could be exhausting. So that's why this paper provides an prototype development of an automated and smart filtration system with a turbidity sensor to detect water quality. And the filtration system uses reverse osmosis to filter out the water, and it's capable of cleaning the fish tank with ease without manual intervention. So that's why we would like to make this particular paper. Why would we think that it's suitable in its filtering system? Why and how does the water get worse? So this prototype work, we will start by explaining how the turbidity sensor work. So first of all, we start our program. That's to power on by turning on the device. Then it will conduct its detection by its dirty water or by that's around the surface of the water. And with checking the dirtiness level, it will conduct if it's whether it's clean or if it's not clean. If it's clean, it will detect the dirty water again, and then it will come down to the checking process, and it will end there. Hence, if it's not clean water, it will turn on the filter and it will directly clean the water inside through the reverse osmosis process. Then it will check the water again. Hence, the checking of the dirtiness level. If it's all conducted to be all clear, it will power off and it will end the system. So the next is about the workflow for the whole prototype. If it's utilizing ESP32 or instead of the Arduino R3, it's basically kind of the same, but with the help of the Blink uh, program. So first, it's going to be start to power on the filtering system. We'll connect to the Blink server and turning all the sensors on. It will detect water, and if it will check the dirtiness level. If the water is dirty, it will conduct the same process again from the first. That's by turning on the water filter, and it will inform the users of the water level and also the uh, the turbidity percentage. Hence, if it's conducting manual request to the filter through the blink, um, it's because of the uh, dirtiness level. If it's the water is detected to be safe, it will automatically go into the power off process, and it will end there. Um, it'll be different if the dirty levels are on the high level. It will conduct to the negative one, and it will start the process of the reverse osmosis until it's iterated to the clean level. Next will be the regression analysis and also the data interpretation that we've conducted from the past experiments. Actually, we can see here from the left side that we use uh, tablespoons to conduct experiments, and the left one to be the time of completion, and blue is the actual data between the time and also the density of the dirt. Sorry, you can see here it's actually going as linear regression. It's really a wonderful data that we can conclude here. Actually, kind of a straight um, line here, making an angle that we can see that it's actually linear from 1 tablespoon to the fifth tablespoon. You can see here from the data interpretation that it's conducted from 1 tablespoon to the five tablespoons. You can see here the water cloudiness level from cloudy to dirty because we only have clean, clear, cloudy, and also dirty. The time here are recorded as follows, with the clarity after the referral osmosis infiltration. You can see here are all clear. Next will be the future AI implementation. You can see here that it's relatively the same. The difference will be the machine learning um, process will be more efficient and more precise rather than actually counting itself. If it's using machine learning, the process and also the actuality of the data will be more precise. So mm, using the send link through the internet, see here, make it compatible, making it compatible with the previous VR3 model. And you can see the analog that we receive in the delivery sensor. We will forward it over the internet, unlike the previous one in the R3. You can see here. By doing so, users can actually control directly with the phone, with the Blink website or application or the app. Since the Blink app supports IoT and ESP32, displaying information will be lots more beneficial if the data is interpreted into real-time information for users. That's why um, be more promising in the machine learning prototype. Next, this is the prototype that we've used using Arduino R3 and plain and local. But the RO or the reverse osmosis process is actually quite intricate um, to be conducted at the same time. The particular models and also the beneficial parts of the osmosis module. Hence, we can conclude that AI will be implemented, of course. You can see by the timing. That time equals to 9.17 times third amount plus 1.62. And you can see that the third amount is the independent variable with the time as the dependent variable. Because time prediction, that amount can be considered as independent variable in the linear regression because it's more likely to be not precisely as one tablespoon or till five, but using supervised learning or regression analysis, this linear regression serves as data sets to train the model to predict the time it takes to clean or the dependent variable. Linear regression that we accumulate and also have seen and also conducted with other papers that it's more accurate and faster for testing on microcontrollers. Also, computational complexity purposes for large data sets. Also, lightweight tree-based models such as gradient boosting done on smaller gateway. Recommended, of course, trained weight, standard deviation, bias, and scalar parameters. So the rich pipeline can be hard-coded on the ESP32 utilizing Python. And also skit learning. Skit learning itself is often necessary in machine learning because many models perform poorly when features differ greatly in scale or distribution rather than being roughly like standard normal distribution more, but helps to ensure that model appropriate weighs each feature. So it's more when conducting directly, it will be more precise. It's very common that features to be significantly different scale. It fits the data and transform to standard distribution where each feature's mean equals to zero. On handling this data, training and also testing should be remain separate, which means never scale the whole data set, but transform some testing data. And this data set or features should allow interactions and predictions. Okay. Next will be the conclusion slide. This is a very early model of device for development of a fully detailed IoT device to be used for taking care of beta fits automatically. The test showed that the device worked well, of course, because using the reverse osmosis that actually integrate directly with the method, utilizing semi-permeable membrane to separate water substances and contaminants, especially when including the machine learning process would be more significantly accurate because it's better in contacting with the Blink app. As I can conclude with the experiment observation and the test. Well, yeah. However, the current device is actually quite in the bare minimum to only automate on filtrations, enough to help in clean water by reverse osmosis. This solution that were given before are a simple help for the pet owners and a significant step towards a well beyond smart and automated beta fish care. Furthermore, proposed applications as predicting the time takes to filter using machine learning predictions and simple linear regression from the data. Also, by using ESP32 for more IoT implementations could be added in future research, as well by efficiency and implications. That's more capable of handling to low to moderate matter. regardless of how the progressively cleaning time is observed, be be more reliable. However, it's not worth noting that maintenance is not required as frequently as usual as in conventional filtration systems, since refers to osmosis as basically more efficient at handling the particles and maintaining long-term performance. Okay, yeah, can actually add more knowledge or material base from the, from the SP32 and also from machine learning processes. Uh, Thank you for listening our presentation and see you next time.